Good morning. It's pretty bright up here. Thanks, Kevin. I've been living in Indiana for 10 years, and I've learned more about Bloomington in the last 10 minutes than in the last 10 years. My name is Nagar Garizi. For those who don't know me, I'm the chemistry leader of the Natural Products Group at Corteva AgriScience. And I wanted to first thank Lisa and the rest of the committee for making this possible. And I'm honored to be here today with you to chair this session. I would like to introduce our first speaker, Professor David Williams. He didn't really want me to mention this, but I find it really impressive that he's been part of the faculty at IU for almost 4 decades. And so during his tenure here, he has trained and graduated many students who have gone on to do great things. And so he has really nourished a very impressive scientific and academic tree during his tenure. And of course, he has received numerous awards, too many for me to list here today, but I wanted to highlight the most recent one, the Ernest Gunther ACS Award in Chemistry of Natural Products. And the title of the award very aptly represents his research interests. So with that, I would like to introduce Professor David Williams.
Thank you very much for the introduction, and thank you all for coming to the 46th National Organic Symposium. We welcome you here to Bloomington. And one thing I want to add to Kevin's comments for you is that if you have time, maybe instead of taking a nap, or in addition to the nap, you'll recognize that the chemistry department is a very large building directly across the street from Alumni Hall, the IMU. And for students here, feel free to browse through the chemistry department, take a look at what we have. World-class facilities for you here in Bloomington. So with my first slide, what I want to do is take this opportunity this morning to talk about the importance of strategy as a vehicle for discovery in organic chemistry. I know through conversations that there are many academicians and industrial leaders who are concerned about how we teach the next generation of students, the next generation of scientists among you, to be problem solvers, right? I hope that I can take this morning to go through some of my own experiences and develop that concept. To be humorous about it, I'll try my tact at humor. It's a little bit like the young father who has his 6-year-old daughter curl up on his lap and say, "Daddy, where do babies come from?" You know, it's that awkward feeling when a graduate student says, "Where do you get your ideas?" Right? Where do ideas come from? And so we want to explore that concept a little bit. And to be sure, we're working against the tide here. Think about it. Most of you as graduate students and as postdocs use electronic drivers to search for recipes. We look at a paper and recognize that retrosynthetic analysis is an executive summary of what the author accomplished, not what the author proposed. These are trends that are very disturbing because E.J. Corey never really sought out the idea of using retrosynthetic analysis as a quick and easy computer-led way to find a successful synthesis. What he wanted to do was identify unique disconnections, opportunities for discovery for the future. So with that, let me go into our slides, and I've got to grab the slide. And talk about the central problem that I want to discuss. And it deals with the daphneocycline alkaloids. These are moderately complex natural products. It isn't the functional group complexity that's overwhelming here. It's really the caged structure where our interest was in daphneocycline A. It has 2 7-membered rings, 2 5-membered rings, and 2 6-membered rings. And all of these are interlocked in a very interesting arrangement. And the question is, how would we actually put these together? In 2001, when Kobayashi actually published the first examples of these natural products, what caught my eye was this central 5-membered ring. a cyclopentadiene that was fully substituted with 5 different appendages. And each one of these molecules contains that 5-membered ring. In fact, these are part of Chinese traditional medicine, and the compounds do show anti-tumor activity, but none of us in this room could possibly say what triggers that activity, what in these structures is responsible for the reactivity that we see in biological systems. And so perhaps there's a good reason why one would want to study these types of molecules. So as a practice, I tell my students, and I'll share with you this idea, I have always kept a notebook, what I call my idea notebook. I started this as an advanced graduate student and continue it to this day, where when I get an idea, I write it in a notebook, and I fill a notebook with all kinds of craziness, and occasionally I review it, and sometimes some of it even begins to make sense to me. I'm going to show you what was an entry in my log in about 2002 or 3 when I first saw those structures. I wrote down this endgame hypothesis, where one could take this alpha iodo-ketone and couple it in what looks like a pretty standard Stille coupling, and in effect join 2 alpha-beta unsaturated enone systems here at their alpha carbons. And then if we could only orientate this molecule with a Lewis acid, a divalent or trivalent Lewis acid with the carbonyls, then a base could deprotonate here. I chose DBU as my executive decision. And you notice that that gives you formally a pentadienyl anion. Well, it's really an enolate, but we can draw it in this one conical form where a 6-electron disrotatory cyclization would then lead to an allyl anion that undergoes oxidation, and you notice that that develops the 5-membered cyclopentadiene, which now has a very low pKa for the hydrogen here at 9 for further deprotonation and acylation to give the natural product directly. So I had in mind this, I thought, very elegant way to end the synthesis. If only I could do this cross-coupling, the rest would happen in one pot, and we would get the natural product. Well, at the time, there wasn't much in the literature about cyclizations, electrocyclizations of pentadienyl anions. In fact, Woodward and Hoffman, of course, proposed that cations, neutral molecules, and carbanions could undergo electrocyclizations, but very little literature spoke of the cyclizations of anions. So we began a program. This started with the work of Jonathan Reeves a number of years ago. You can see that it's quite dated, and I apologize for going back to 2006, but I want to demonstrate the point. He chose this type of system as his model, and through the addition of an organolithium reagent at this carbon, he generated the contiguous array of 5 carbon atoms with 6 electrons in the pentadienyl anion. Now, we did this study in the NMR tube at low temperature, and at minus 78 degrees, you could see that the first reaction happened rapidly. And then as you warmed the probe, you would see this material turning into this material at minus 35 degrees. And in fact, later we found that we could quench this allyl anion with a variety of electrophiles. You see, of the 20 examples from this paper, you see 6 of them here. All of these things were successful. In addition, we chose this example. This was a kind of, I would say, a really risky operation, because the addition of the lithium reagent here would necessarily make a pentadienyl anion where the ring closure would make a very strained 5-3 system, this bridge system. And in fact, in the NMR, you don't see any of this at all. You only see this. Well, that's because of microscopic reversibility. This can go back and forth, of course, as predicted from the Woodward-Hoffman rules. But we had placed this methoxy group at this location. And because the allyl anion is developed, then it can eliminate, and in fact, the only product of the reaction was this material. So we could trap out, if you will, the cyclized and more strained product out of the reaction. So we have some basis for thinking that perhaps we can carry out these types of reactions, and it was actually many years later that we decided to go forward with the synthesis of this tricyclic component as an advanced intermediate for my endgame approach. So I'm going to tell you now about how we tackled the stereochemistry and the enantioselectivity in making this particular material. I'll point out I've labeled 5 and 6, these two carbons. Carbon 5 is a quaternary, as we say, quat carbon, a fully substituted asymmetric carbon, and those are necessarily sometimes difficult to put in. And I'm going to show you a scheme that allows us to fix the stereochemistry at 5 as well as 6. Well, this started simply enough with some well-known chemistry using the CBS reduction of the ketone to give this allylic alcohol with high EE, and then an acylation reaction with the carboxylic acid provided this ester. And from there, we deprotonated kinetically to make the EO enolate and carry out the Ireland-Claisen routine, which necessarily sets that stereochemistry. Now, the product, carboxylic acid, was turned into the ester, and then a dibal reduction provided this alcohol for subsequent removal of the double bond that you see here. We ran into a first problem there. Interestingly enough, palladium on carbon carries out not only a reduction of the double bond, but also hydrogenolysis of the CO bond and the loss of the O-mom group. And so to avoid that, we found that we could add ethylene diamine. Our first problem was overcome, and then clearly we reduced only the double bond, retaining the O-mom. The ley oxidation proceeded as expected, and then reductive amination with the amine here gave us the product that you see over here after protection with FMOC. So we don't have any rings yet, but we have put in 2 of the stereo centers. Our first ring was made, as you see on this slide, where we're going to use ring closing metathesis. This begins by removal of the O-mom group with testriflate and bipyridine. It doesn't affect any of the other protecting groups. And from there, an IBX oxidation and the addition of divinyl zinc occurs in an asymmetric fashion with the addition of this ligand. And this uses the beautiful chemistry developed by Oppolzer. I gave you a reference going back to 1991. And of course, Andy Myers has developed this more beautifully in a paper in 2007. So we get a wonderful serial control of 88 to 12, diastereo control at this center in the formation of an allylic alcohol, and from there we can protect this as TBS. DDQ removes the PMB group selectively from here, doesn't touch this one. Again, the ley oxidation gives rise to the aldehyde. The addition of vinyl Grignard gives a mixture of diastereomeric allylic alcohols. And then the further oxidation with Des-Martin reagent gives this reactive enone. This enone is a beautiful substrate for ring-closing metathesis, almost in quantitative yield, very 95% yield. This gives formation of the 7-membered cycloheptenone with the 3 chiral centers already installed. From that point, we're going to make a higher order cuprate for the addition into the enone here. That occurs from the side of less steric hindrance, the downside, to give the installation of this allylic silane. And from there, we're going to close up the second ring using a reductive amination. Now, the addition of triethylamine in here removes the FMOC. That's the role of the triethylamine. But from there, the amine immediately adds into this ketone. And in fact, what you see in the NMR is the hemiaminal. You never see the ketone. So not surprisingly, when you add into this mixture the sodium triacetoxyborohydride, you get reduction to the cis-fused 5-membered amine. And that material was used for bromination at minus 78 degrees because you would expect that the allylic silane will give rise to the transposed allylic bromide. Due to symmetry, it doesn't matter. And the amine that's present undergoes a displacement of the bromide to actually give you this 6-membered ring formation as the quaternary ammonium salt. So we have our 3 rings formed, and furthermore, we can use a brief contact with 1 normal HCl to remove the TBS group, and then the IBX oxidation to oxidize to the ketone. So in a fairly straight order, we could make this ABC system of the natural product. And now what we want to do is a reduction of the double bond here. This is a stereochemistry at C18 in the daphneocycline A molecule, and this has been a problem. If you just do a reduction with palladium on carbon, you get about a 3-to-1 ratio of diastereomers at that position. So instead, we chose to investigate directed hydrogenations. There's much in the literature about using hydroxyl groups to direct a catalyst to reduce the double bond. More recently, people have looked at other functional groups. We have chosen a ketone as our directing group, and that is quite unique. You'll notice from my ball and stick model here that here's the ketone canting into the back of the screen, and it is positioned below the double bond. So not surprisingly, as our cationic catalyst binds to either of the lone pairs of the ketone, it brings the rhodium catalyst directly into the neighborhood underneath that methylene group, and then the reduction gives exclusively what we want, the correct C18 stereochemistry. There's the DR. This is a really very efficient reaction, and I give you this example from Ang Lee's work in 2017, where he has used an amide carbonyl, a more nucleophilic carbonyl, as a directing group as well. From there, LDA was our choice of a base to deprotonate kinetically at this position, alpha to the ketone. But sometimes synthetic planning doesn't go as you expected, right? You discover new things. And we had placed this quaternary ammonium salt in there as kind of a protecting group for the amine, because we have to do oxidation chemistry, and we don't want the amine to be oxidized. So it seemed like a good way to protect that nitrogen. But in fact, under these conditions, you notice we found that we kinetically deprotonate here. And quenching the reaction doesn't make the silyl-enol ether, but instead you end up with the allylic silane as the only product. Some interesting chemistry. Kind of put that in the back of your mind of things you might be able to do with that later. In addition, we tried to functionalize this cyclopentene, heptenone, by bromination. And here I just want to show you that by reading the literature, and Phil Barron is a huge fan of this. Go back and know all the old literature, because you can find really unique things, right? We found a paper in the Canadian Journal of Chemistry in 1969 that tells us about a reagent, this reagent right here, it's right here over the arrow, which is a powder, kind of a dark reddish powder. I'm not even sure of the structure of it. And what it's reported to do is that it allows you to brominate alpha to a ketone without brominating a double bond within the structure. Think about that. That's an amazing selective process. Well, we chose that, and it was reported that perhaps this went through the enol rather than an enolate or something like that. And so we found success by actually generating a single diastereomer as the beta bromo ketone is the product. And that material was a rock. You couldn't really do much with it. It didn't react well at all. However, if you added DBU and let this stir overnight at room temperature, you found that it would undergo polymerization at that site and give this compound, which was very labile. That one undergoes a classic E2 elimination because it's aligned correctly and eliminates to give the alpha-beta unsaturated ketone. So we're getting there. We're beginning to think about how we can get to that end game that I first proposed to you. In fact, we have found that we can remove the PMB group from here in 2 different ways, by hydrogenation or by use of a thiol as a nucleophile to remove the PMB. And either of those reactions gives rise to the ketone now bearing the tertiary amine, and that compound can be deprotonated with bases. Now, it wasn't straightforward, and LDA wasn't successful, and a host of other bases did not work, but we found that potassium hexamethyl disilazid at minus 78 degrees would allow us to deprotonate and access the enolate. Quenching with this Davis oxaziridine gives you the alpha hydroxy ketone. And by the way, it also oxidizes the amine to the N oxide. But we can remove the N oxide by using B-pin, this dibepin. And quantitatively, that takes us back to the amine. And so then with a second oxidation, using this nitrile radical, we're able to, and by the way, I left off the disopropyl azodicarboxylate here as the stoichiometric oxidant for the reaction. This is merely a catalytic oxidant. And that gives rise to this alpha hydroxy cyclopentenone, and that has the handle on it that we will need to modify and carry out our coupling reaction. All right? There are other ways that perhaps we can build out that five-membered ring of the natural product, and I'll show you that in this case we carry out an acylation reaction using excess potassium hexamethyl disilazid, and that gives us this enol, again, for functionalization. And we've even been able to do simple aldol reactions followed by oxidation to make the 1,3-diketone. But what I want to do this morning is go on with this idea. Remember, this was the plan, right? And I've already talked about problem solving in natural product chemistry and how important that is in terms of your overall strategy. We thought this was going to be easy. Not so. In fact, here's a table, and I apologize for using a table, but we started out doing this with the classic types of catalyst, tetrakis, and all the other things. And what we found, I'm going to summarize quickly, is that any phosphine ligand gave you zero yield. I mean zero. Didn't react at all. Right? I'll take you down to this line number 4. You notice we chose a palladium catalyst now that avoids the phosphine ligand, and then we added a ligand over here, and of course we got zero as a product. It wasn't until we got to item number 5, entry 5, where we used the tetrabutyl ammonium iodide, and this is reported to make nanoparticles, right? This is a procedure by which you get to nanoparticles. Then we started to see reactions actually occur. Ultimately, it's the highlighted entry 6 that after about 9 months led to success. We now have a general reaction that links two alpha-beta unsaturated systems together at their alpha and alpha prime carbons, respectively. Well, I can show you just some of the examples. And truly, when you solve a problem, it's supposed to be general. So we can link ketones with ketones, esters with esters, esters with ketones, amides with esters, aldehydes with ketones and esters, etc. And here are 9 examples of about 20 that we've done, right? What's even more important is that the geometry of the double bonds that are contained in these alpha-beta unsaturated systems are retained largely in the product materials. There's one exception we ran into, and that was with an iodide that was a simple compound. And I think it had an ethyl group here. And that compound isomerizes just on standing at room temperature. And so, of course, we're running the reactions at elevated temperatures, and the product mixture of double bond isomers reflected the equilibration of the double bond of that segment. However, we're able to make all of these materials and even take this into perhaps more useful chemistry using the Suzuki coupling. So I have some examples here. Of course, here's the B-pin derivative that will couple with either a triflate or iodide, and again, we'll make this cross-conjugated bisenone that you see as a product. There is a but in this. You know, I emphasized, and everybody, you know, especially in industry, you know, I show tin on the slide, and they say, "Oh God, why do we don't want to use tin? Boron is more user-friendly." That's true. But with tin, you can actually make the E and Z geometries of the double bonds with high integrity, and you can chromatograph them to know that you'll have only one. But we found in practice that with making the B-pin derivatives, it's much more difficult. You can make the esters, but compounds like the aldehydes, for example, or the ketones are much more labile and more difficult to deal with. This is one that's fixed because of the six-membered ring, so it was easy. And it led us to make some compounds that are incredibly reactive. Take a look at this one. What I want to focus your attention on now is something we recognized. First of all, these two enone systems, let's look at it as a diene. It's really electron deficient, right? It would want to trap nucleophiles readily. And furthermore, the two systems are not planar. The structure you draw on the screen is a lie. They're really orthogonal to each other. They lie at 90 degrees to each other. So in thinking about this, it stimulated yet another idea, and that was that perhaps we could instigate an addition to these things, a nucleophilic addition, using an enamine. I'm going to use an indole, and we're going to use a magbromide as a Lewis acid to instigate all of that. The addition happens to the enone system that's most reactive. That's the first addition, a 1,4 Michael addition, if you will. And that gives rise to an iminium ion and a magnesium enolate, which then comes back and traps the iminium ion to give a six-membered ring. This is a formal 4+2 cycloaddition, but it is by no means a concerted process. It is a cascade of a Michael reaction, a reversible Michael reaction, followed by a manic ring closure, and you get a single stereoisomer with the generation of 3 asymmetric centers. All right? You see my quote up here, and I've had a sprinkle through here a number of quotes. And this one I like a lot for you students and postdocs. I think as a postdoc, back in my days at Harvard, I was insanely crazy about trying to figure out how to generate ideas, and I actually started keeping postcards that I could write on, blanks, next to the bedside, so that if I woke up in the middle of the night with an idea, I could write it down, right? I don't know how, probably most of it was gibberish, but I actually have gotten ideas in the shower before. So, and so there's some clues to how you might be able to think about your chemistry, maybe even while dreaming about it at night. And as a second-year graduate student, you're probably already experiencing dreams about chemistry, I dare say. Okay, well, it turns out that this is a one-step convergent route that makes these tetrahydrocarbazoles. Tetrahydrocarbazoles are unique natural products that are everywhere. There's thousands and thousands of examples of these things. Furthermore, we could do a DDQ oxidation to oxidize the ABC ring, this ring here, to the aromatic case, and not even remove the P and B from the alcohol. And here's some examples. You can see that you can incorporate some unique functionality. If you have the C2 substitution on the indole, well, the yield goes way down, but think of the steric congestion that you've generated in this more complicated species that you've made. And you can carry along an alkyl, small alkyl group on the nitrogen of the indole itself, and that seems to have no effect. You can readily make these types of materials. I want to switch gears just a little bit. You know, you don't have just one idea. You have versions of ideas, right? And one of those versions we had for our cyclization, I think is still relevant today. I think it's something that still attracts my attention because we thought perhaps maybe we could do a cross-coupling that would make this conjugated allene. And if we made the allene, then maybe we could find an organometallic reagent. I call it nuke metal, right? A nucleophilic organometallic reagent that would add the nucleophile to the central carbon of the allene. And if we did that, we'd necessarily make a pentadienyl system that would be complexed with the metal. You can take that in your mind anywhere you want. In our original electrocyclizations, we did calculations of this type of intermediate, and the lithium sits uniquely over the top of the pi system directly between the two termini. That's what we know about the lithium. So it would make sense that maybe some other much fancier transition metal would do the same. And then if it collapsed to form a bond, well, the metal would end up associated with the oxygen of the enolate that would be produced in the reaction. And this might be an interesting way to make that 5-membered ring system. Well, I had another idea that came out of this, and that was, what if this wasn't OR? What if this was tethered to an alkyne? This was tethered to an alkyne. Now we set up what is a classic reaction mechanism. It is the Poisson-Kahn reaction. Utilizing transition metal complexes of carbon monoxide, you can insert the carbon monoxide here in a 2 + 2 + 1 cycloaddition, making a 5-membered ring, a bond across here, and a new cyclopentanone. For sure, there is loads of work out there. The original Poisson-Kahn reaction wasn't terribly successful, but I'm going to give you some names. Kay Brumman, who's here at the conference, has been a pioneer in developing all kinds of new and more interesting intramolecular Poisson-Kahn reactions. This is just one of her papers. I could have filled a slide with all of the papers she's produced in this area. In addition, I'm going to jump down here to Andrew Evans. Andrew Evans has taken up the task of studying rhodium and how rhodium can affect the Poisson-Kahn reaction. Has done some intriguing mechanistic work in this area as well. And finally, I would be not very diligent if I didn't include Steve Buchwald, our Adams awardee. Steve used the titanosine catalyzed CO insertion to actually develop a Poisson-Kahn mechanism using a unique metal back in 1996. Well, this looked too good to pass up, right? It said, if I could just make this thing, I could make this 5-membered ring, and then maybe develop an aromatic ring in here and elaborate the 5-membered ring to this, and that would give me a natural product. That looks like something we should try. Again, there's a but. But the Poisson-Kahn reaction, as we know it, the scope and utility of it never really made it into the area of dealing with nitrogen heterocycles. What if this ring contained a basic nitrogen? Wouldn't that just bind the metal, the transition metal? And well, there weren't any examples of successful Poisson-Kahns using this type of tactic, especially with cobalt carbonyl, the preferred reagent for that reaction. So we began our studies. Here's our retrosynthetic analysis, and mindful of what I said before, it's not going to bear a direct relationship to what we actually achieved, but going from this precursor, here's our aldene tethered to the alkyne, our Poisson-Kahn would give this material with the oxazole, and then we could do an aldol condensation in here and a Heck reaction to close and make the aromatic ring, and from there, a conjugate addition and methylation, well, that would lead all to this marine natural product, and wouldn't that be wonderful? We even found support for the idea that we could make the aldene really effectively. And that came from the idea of using a propergillic stannane and doing a coupling. You see it here with this 5-iodo-oxazole. It has an iodide, a bromide, and even the 2-thiol, which is reactive in cross-coupling reactions, more reactive than the bromide, in fact. But it was the iodide that led the way, and we got only coupling from the internal carbon to give rise to the aldene as the exclusive product. And it worked also even better in this case, where again we make the aldene, and now we can chop off the protecting group and carry out an O'Hara-Bestman reaction to install the alkyne, and you can see we're ready to go. This is going to work. Well, there is another big stumbling block, and that was when we first tried these Poisson-Kahn reactions with cobalt carbonyl, tungsten carbonyl, and I could go on and on with many others. None of them worked. None of them worked at all. And it wasn't until my student tried iron nonacarbonyl that we found that we got a reaction to work. And this reaction required NMO as an additive. It was quite unique because the Poisson-Kahn reaction necessarily takes the starting material and puts it in a bomb, a stainless steel reaction vessel, uses CO as a gas with a pressure applied to and then heats it at 170 degrees. And you notice we were actually putting this reagent together at -50 and warming it to room temperature, and it worked. The reaction was successful. It was successful, and in fact, it even gave us regio control in the geometry. You notice the R3 substituent on the alkyne is always at the alpha carbon primarily. These ratios indicate that a little bit, maybe 7, 8% or so, maybe less, would occur with this regio isomer. The stereochemistry of the remaining double bond remained intact, however. And furthermore, this was so mild, it allowed us to incorporate all kinds of sensitive functionality. Look at these two things. Here we have a stannane that's been incorporated in the 2+2+1 cyclization, ready to go for my dreamed of coupling reaction that I want to use for further chemistry. Well, I've given you some references for early precedents. Narasaka, by the way, is often cited for his use of this iron nonacarbonyl. He used it in photochemistry, a photochemical reaction, as opposed to the Poisson-Kahn conditions that you see here. A funny thing happened on the way to generate all these products. We always saw a product, it seemed like a byproduct, that appeared on a TLC plate, and it was seemingly stable. It was always formed about 5 to 10% or so, and my student isolated it. And he found out that it was an iron complex, and he could take that iron complex and put it in with more alkyne, and it was reaction competent. It would generate product. Wow. So now we have to find out what this complex is. We ultimately made a fairly complex and sterically hindered substrate, and that gave us crystals, a crystal that was uniquely this 3-membered iron metallocycle. No one had seen any of those before. When you think about it, it's pretty obvious that the Lewis acidity of this reagent may complex with the double bond and make a pi complex, but would a pi complex actually be a stable entity? It appears so. Here's the X-ray. We went on to make these 3 additional ones, and each one of these could be isolated after running it down a flash column, and furthermore, you could characterize it by NMR. These give beautiful NMR spectra. And so we have a very unique intermediate. I want to tell you about what we did computationally to explore the reactivity of this 3-membered iron, I call it iron cyclopropane. Right? What happens is that the NMO, as an oxidant, is going to burn off one of these CO ligands. It's going to make CO2, and that's downhill by 50 kilojoules. It's huge, right? And that gives you an open coordination site on the iron for complexation of the terminal alkyne. Here I show the TMS group as a surrogate for any functional group, alkyl group. And you notice that that's going to make this, I guess, some kind of pi complex. Let's talk about what that really looks like. There are 2 possible structures. I've written them down here as A or B. In A, you notice that we have, here's the 3-membered ring that was formed by the addition to the allene. Here's a kind of 3-membered ring that represents the pi complex to the alkyne. And as I tell students, this is a piano stool structure. The 3 COs here, here, and here are pointing to the back of the screen. And if you think about a butterfly, it's like the wings of the butterfly are pointed up. These 2 sets of carbons are pointed to the top side of the molecule. This brings C2 and C4 close together within bonding distance. And that's your insertion reaction that leads on to the next step. On the other hand, here's the other opportunity. This compound would be an isomer of that, where the 3 COs ring around the structure and the butterfly's wings are out to the side, right? In this case, C3 and C4 are too far apart for bonding. This is the structure that represents this intermediate. And of course, this is the structure that leads to insertion. You find then the formation of this A-3 complex of iron, insertion of a CO, formation of a 6-membered ring, and reductive elimination to form the 5-membered cyclopentenone. I'm talking in terms of cross-coupling here. And why I'm talking about it in those terms is that for you as students, you think about a catalytic cycle, it's a circle, and people have reagents flying off the sides, and they go around. But has anyone said to you, yeah, what's the stereochemistry at the metal? Hugh Davies is concerned about that. We're going to hear from him later, right? And for those of you that are just starting your careers, this is going to be a big opportunity for the future. Carbon has stereochemistry, so do metals, and it matters. Okay, let's breeze through this synthesis. I'm almost finished. We're going to use the iron carbonyl to carry out this cyclization. It works. We deprotect the mom, we oxidize with the swern, and then with base, this immediately closes up and aromatizes to give our 6-membered ring. Furthermore, we can use a page, actually this comes from, it's not identical to, but it's a kind of a modification of work by Steve Buchwald, in which copper hydride is going to add to C4 asymmetrically to give the down hydrogen. We tried to methylate that enolate directly, but you cannot because it's too stable. So therefore, we methenylated again here and then used super copper hydride. This is a procedure from Bruce Lipschutz to carry out the second addition, and that thermodynamically gives you the down methyl group at C11. And from there, 3 steps, again, gave us the natural product. I'm going to close with just one more slide, and this is my slide. We talked about this cross-coupling of iodides with propergillic stannane, and we said this is a way to make allenes. So if we do that coupling, well, now we make this material. We made the 5, the 6, and the 7. And then, well, we said, well, let's try to do a cyclization like we did with the indoles. If we add indole to this, not only does the first one add here, and again initiated by mag bromide, to give the corresponding magnesium enolate and the iminium ion for ring closure to make the 6-membered ring. Remember, that's our Michael-Mannick combo. And that goes with stereo control, but the product now is a conjugated system. And the second equivalent of indole adds in here and gives us these products, these more complicated, I call them bis-indole derivatives, as products of the reaction. Okay, what's my takeaway from this? The forefront of organic chemistry for the future is how you can build molecular complexity efficiently. That's the real battleground for the future, right? It isn't how to make more simple molecules, it's how to make more complicated molecules with greater efficiency. I've just shown you 3 steps, a Baylis-Hillman, a cross-coupling, and cyclization to make that. 3 steps with complete stereo control. Okay, I've summarized. I'm not going to say more about the details of what I've shown you, but I've kind of used bullet points to tick off some of the highlights of what we went through this morning. And I have to credit the people, of course, who did all of the work. Their names appear on this slide, Seth, Jonathan Reeves, and Seth, Akshay Shah, who did the iliapithoxazole synthesis. And, of course, other people in the group who intellectually lent themselves to the development of these projects, of the thought processes. I see students these days going in the lab working as solitary investigators with earphones and not talking to any of their peers. Talk to your peers over lunch. Use napkins to draw out structures and come up with ideas. Share your thoughts. It's really important to how you develop as a scientist. I finally want to conclude with this quote. I've said I've sprinkled some quotes through the slide, and I hope you've enjoyed those. But this one comes from a famous English author and philosopher more than a century ago. And He said, the dignity of the artist lies in his duty of keeping awake the sense of wonder in the world. Pardon his use of his or her certainly would be appropriate. And even in his time, there were some very famous poets and authors who were women. But I took the liberty of crossing out artists and putting scientists up here, because we could say the same thing about each one of you and the opportunities you have to inspire future generations of how they think about chemistry and advance the field of organic chemistry in particular. Thank you very much for your attention.
Hi, thank you for your talk. My question is actually on the very last slide that you gave. And I was wondering if you could comment.
Repeat that very last.
The bis indols slide that you closed with.
Okay.
And I was wondering if you could comment as to why the 7-membered rings stopped at the mono indole.
I didn't. I'm sorry. I skipped by that quite inappropriately. We limited the amount of indole to see if we could do that, and we were able to actually stop at that one point. And the inference is that maybe you could add a second nucleophile, not just indole, but something else to that system and engage it further. So we haven't explored that, by the way, but that's the idea.
Thank you.
Any other questions? I thought I saw. Could you please also state your name and your institution? That would be helpful. Thank you.
Hi, Andy Evans, Queens. Nice job, Dave. In the POS and CAN kind of chemistry, did you look at any olefins doing that same chemistry? Because olefins are quite tricky, and what you've accomplished in that is really quite a challenging reaction, is that doing the intermolecular reaction is very, very challenging. Most people revert to the intramolecular to get around the regiochemistry problem, which that beautifully solves. So I'm wondering whether you pushed it further and then you could get stereochemistry out of that reaction.
Professor Evans is quite right when he talks about the case for the intermolecular reaction. In the POS and CAN, the scope and limitations of the POS and CAN reaction, most people have actually focused on the intramolecular reactions, and one could even make the argument that those are really valuable because you make 2 rings at once. But POS and CAN were not able to actually successfully carry out an intermolecular reaction. Very, very low yields in that report, as I recall, right, Andy? So there is room to make further advances in that area. Now, in our case, we haven't looked at standard olefins, isolated olefins. We've only looked at allenes. And I suspect that the allene is just much more reactive in making that organometallic complex. I can't hear you.
I think about the other component. So once you bound the ion to the allene, have you thrown in an alkene rather than an alkyne? So
I'm sorry. Excuse me. I didn't. No, we have not.
Yeah, because it forms this complex.
Yes.
And you're using stoichiometric ion, there's a good propensity that will react.
You are quite right.
And one of the other challenges with these reactions as well, which people gloss over, is that when you substitute the olefins, the reactivity drops off a cliff. Yeah. And if you look in the literature, there are very, very few substitute olefins. They're generally terminal olefins.
Yep. Yeah, good point. I'm sorry, I misunderstood your original question. Yeah.
Hi, Ron Brisbois, McAllister College. So you showed us that unexpected protonation silation of the quaternary ammonium protecting group.
Yes. And
you asked us to think about what you might do with those. So you have that allenyl silane. What have you done with those? Have you? We haven't. We've tracked on. We got away from that and said, let's go forward with trying to, do our synthesis, and we haven't gone back to the idea that we could make Sakurai reactions come to mind right away. Exactly. We could dealkylate the amine, and we'd have an enamine ready to go to do additional chemistry. We have not explored that at all. Or, could possibly even tie into some of Danheiser or Meyer's chemistry with 3+2s at that position. You absolutely bring on another ring, it seems.
Absolutely. Yeah.
Dave, this is Kay Brummond. Congratulations on a very nice presentation and also on a successful
Where is she?
iron-mediated Poisson-Kahn reaction.
Okay.
So I was looking at your molecular orbitals that you, well, actually I was thinking about the molecular orbitals for the iron complex that you had. And for the two structures, one is the piano stool structure that you had drawn, and then the other was the trigonal bipyramidal iron species. So in looking at those, I guess just from the audience, it looks like the orbital overlap of the two alkenes that are coupling actually differ too. So
Yes.
is that the case, or was it just a distance?
You are correct. They differ. And in fact, I will send you to the paper. So we've published a paper on this with the help of Mookie Bake as our collaborator for the computational part. And he looks uniquely at each of these ligands in how they activate the iron. So in some cases, you can see donation from the ligand, and also the proximity of the orbitals on the olefin and how they're arranged in order to give rise to the, I called it insertion reaction, to lead on to the product.
Okay.
That is correct.
Thank you.
Sir, one of the olefins at room temperature, you said your room temperature or higher temperature is isomerizing. But in the case of olefin, in the case of solution or solid state, if you pass light, it isomerizes. But in the case of your reactions, you mentioned that at room temperature, one of the olefins isomerizes. What reagent causes that isomerization? And does that isomerization cause any issue with the desired product? How it is going to affect?
What's he?
Is my question clear to you?
No, I'm sorry.
Okay. Okay.
You're talking about the iron complexes?
One of the olefins used for the reactions, I mean, there are so many olefins used, but one of the olefins that isomerizes not by passing light. If you pass light in solid state and solution, it isomerizes. But with room temperature, one of the reagents causes, or I don't know whether it's a higher temperature isomerizes.
Yeah. So is he talking about the alpha iodo?
Olefin.
Alpha iodo olefin?
No, it's a kind of olefins you're using for
Which one?
kind of. One of the in the middle of the slides, it's not exactly lost or. Okay.
So in the cross-coupling reactions to make the bis enons.
Yeah, you're right. Yep.
Oh, okay. So in that case, we have an example of a, I can't remember whether it was an E or Z alpha iodo ketone. Yeah. And we found that material is easily isomerized just on standing at room temperature, such that you can't control the geometry of it very well. And frankly, we don't know. It could be, you're right, it could be the fluorescent lights in the hood. It could be that there's a small amount of iodide radical that's produced, and then that's causing the isomerization. We never really solved that problem. We went on to more stable entities and worked with those. And this material was uniquely problematic because it was low molecular weight material to begin with. So, getting it into a reaction where we could stabilize it, and going to lower temperatures, by the way, was not successful. We needed to heat to about 70 degrees to see the successful cross-coupling take place. So we were defeated by the fact that the material, this low molecular weight iodide, would readily isomerize between E and Z isomers.
Does that affect your desired product? I mean, does it have any impact on the product formation?
Is that published?
No,
Yes, yes it is. See me later, and I will give you a reference for that.
Okay.
Okay.
Thank you.
So for the purposes of keeping us on time, we will finish the questioning portion. And let's thank Professor Williams again for a great talk. Thank you.